Welcome back. This is Part 2A, an overview of the four-step travel demand modeling, or TDM, and travel demand forecasting, or TDF process. We are continuing in Module 02, Data for the Planning Process. This module is presented by Professor Mohan Venagala and rendered in AI-generated voice. A reminder that this material is copyright protected. Where does the TDM process fit? Urban planning focuses on city structures. Transportation planning, which is a part of the urban planning, develops multimodal systems. Travel demand forecasting, or TDF, is the core component of transportation planning that predicts travel patterns and volumes. Travel demand forecasting, or TDF, is the science of replicating current travel behavior and predicting future travel demand. At its core, TDF models the balance between urban activity, which is the demand, the people, jobs, and housing, and the networks, which is the supply, the highways, and transit lines. The traditional TDF process begins at the household level, driven by demographics. This is constrained by infrastructure and ultimately manifests as demand, resulting in traffic volume and transit ridership. Our goal is to model the interaction between the human desire to move, demand, and the physical capacity to move them, supply. By doing so, we can first identify deficiencies in the current system, then develop solutions for short-term improvements, and finally, plan for future growth by forecasting future demand. The figure illustrates this interactive system. As mentioned earlier in Module 1, the green box is the main focus of this course. The forecasting flow takes urban activity and network data as inputs. The process is travel demand forecasting, and the outputs are the flow volumes and system performance. This flow chart on the right expands on the previous illustration. It summarizes the four-step process and specific steps at which the interaction between supply and demand. The most common approach is the four-step model, also known as the sequential method, because the outputs from one step become the inputs for the next. The four steps are: 1. Trip generation. How many trips are made? 2. Trip distribution. Where do they go? 3. Mode usage. How do they travel? Auto, bus, rail. And 4. Traffic assignment. Which route do they take? TDM is a complete process. We study behavior using surveys to understand household choices. We replicate reality by creating mathematical models of that behavior. We create a digital representation by simulating the transportation system in a computer. And finally, we use it for scenario testing, running what-if analyses for future planning or proposed projects. TDM is about studying travel behavior at the household level, replicating elements of travel behavior as empirical and computer models to estimate travel demand, digitally representing the transportation system attributes such as road networks, modeling and studying the interaction of travel demand with the transportation system, first by replicating the current conditions accurately, and then by creating and modeling future scenarios, identifying deficiencies, and then finally, developing solutions. The figure on the right illustrates this complex processes at play. The four steps of the model are designed to address the four key travel decisions that every tripmaker must resolve. 1. Decision to trip is handled by trip generation. 2. Decision on where is handled by trip distribution. 3. Decision on how is handled by mode split. And 4. Decision on route is handled by traffic assignment. These four steps model all four different decisions. As we get into the details, we need to clarify some basic vocabulary. A person trip is one person moving from A to B. A vehicle trip is one vehicle moving, which could contain many people. And every trip has a trip purpose, such as work, shop, school, or other. Here is an extreme example to illustrate the difference. In this case, there is only one vehicle trip, but there are potentially scores of person trips. This slide marks a mini workshop we would conduct in class, focusing on the concepts of productions and attractions, which students often confuse with origins and destinations. There are two important rules to remember. For home-based trips, if one end is home, the home end is always the production, and the non-home end is always the attraction. For non-home-based trips, where neither end is home, the origin is the production, and the destination is the attraction. Also remember, by default, when we say trip, we mean person trip. A key concept is linked trips or trip chaining. For example, dropping off a child at school on the way to work is technically two separate trips, but it is often modeled as a single tour to understand the true connected travel pattern. Same is the case when you drop off your car at a park and ride lot and then take a bus to work. It is usually considered one transit trip. We analyze movement as either distinct trips or connected tours. Note that each arrow represents a single trip, and the direction of those trips is heavily dependent on the time of day, like the morning commute versus the evening commute. Each person who makes a trip in a household has a schedule for each day, which is the first part of the illustration. For a typical person, his or her schedule begins in the morning at home, and ends after the last trip of the day is made. The person need not be the drive. The schedule of each person can be divided into individual tours. A tour is a set of trips that begin and end at home. As you can see in the illustration, one schedule can have multiple tours. Likewise, as you see in the third part of the illustration, a schedule can be divided into individual trips, with each trip having 2 trip ends. The 3 primary approaches are the trip-based model, which treats each trip independently and is our focus, the tour-based model, which links trips into chains like home, workshop, home, and the activity-based model, which models the entire daily schedule of activities. Again, we will be studying the trip-based model in detail, where each arrow represents a trip and the direction is time-dependent. The 4-step model is fundamentally a trip-based method, organizing demand based on the trip purpose, home-based work, home-based shopping, non-home-based, and home-based other, which feed into the 4 sequential behavioral steps we've discussed. There are several flow diagrams that depict the 4-step TDM process. This is the most simplified version. It shows the flow from the initial urban activity and networks to the final assignment. This is an alternative visualization, emphasizing the flow from the initial land use decisions all the way through to the final network loading. The source for this is de Souza. For a more comprehensive illustration of the framework, we look to the National Cooperative Highway Research Program, specifically the NCHRP 365 and 716 reports, which elaborate on this process in much greater detail. We will primarily use this NCHRP framework throughout the course. It is standardized, comprehensive, and includes essential steps like feedback loops and validation that are critical for a realistic model. Before the first step, trip generation, we have a setup phase. The entire urban area is divided into traffic analysis zones, or TAZs. We must reduce all of our data, including demographics like population and economics like employment, to this specific TAZ level for modeling purposes. We now move into step 1, trip generation. The foundation for this step is the traffic analysis zone, or TAZ, level data we just discussed. Using the demographic and economic data, such as population and employment, collected for each TAZ, we calculate the number of trips produced and attracted by that zone. This answers the fundamental question: how many trips are starting and ending in each area? In this example, the trip generation step determined that Zone 1 has 1,633 productions and 4,522 attractions. Next, we have Step 2, trip distribution. We transition from knowing how many trips are made to determining where they go. The productions and attractions calculated in Step 1 are now distributed to all other TAZs in the study area. This distribution process uses system attributes, primarily the travel times or generalized costs on the network, to determine the most likely destinations for those trips. In the example shown, Zone 1 has 1,633 production ends and 4,511 attraction ends. Some of these trip productions will go to the match with attractions in other zones. Those are called intra-zonal trips, meaning they travel from one zone to the other. Some of productions in Zone 1 will meet the attractions within Zone 1, which means that these trips will be completely intrazonal. This process of matching productions and attractions is called trip distribution. Step 3 is mode split. This step addresses the question: how do they travel? The distributed trips between TAZ pairs are split based on the traveler's choice of transportation mode: auto, transit, or non-motorized. Crucially, mode split converts the initial person trips into vehicle trips, which is necessary for the final stage of loading the physical network. In the example given, 200 of the 1,633 trips produced in Zone 1 were attracted by Zone 5. This pairing was done in Step 2, trips distribution. Of those trips to Zone 5, the mode split step determined that 175 went by car and 25 went by bus. Finally, we reach Step 4, traffic assignment. A series of steps apportion trips by time of day, and then convert person trips to vehicle trips. The traffic assignment process assigns vehicle trips to specific routes on the highway and person trips to transit networks. The end result is the loaded network, which shows the estimated flow and performance of the system. The figure illustrates the loaded network for Tucson, Arizona urban area. The color-coded links on the map illustrate key metrics like traffic volumes, speeds, or the level of service, loss, on each segment of the roadway. Before moving on, we must emphasize that TDM is a data-intensive process. To build an accurate, realistic model, we need extensive data across 4 main categories. These include the transportation system itself, socioeconomic conditions of the area, user activity, how people travel, and current system usage, what is observed today. We break down these essential data needs into 4 categories for the remainder of this module. Part 2B will cover system data, which includes defining study boundaries, creating traffic analysis zones, TAZ, and modeling the networks, both highway and transit. Part 2C is dedicated to socioeconomic information, primarily focused on demographics like population and data on employment. Part 2D focuses on activity data, which is how we capture actual travel behavior, mostly through surveys and travel diaries. Part 2E reviews other data used for validation and calibration, such as observed traffic counts, cordon counts, and transit ridership figures. That concludes Part 2A. In the next video, we will discuss the needs, sources, and methods for system data.